All right, so we'll pass it over to Dave for a discussion on lake houses and data lakes.
Cool. Thanks, John. I'm gonna share my screen here.
Coming through?
Is this still there?
Yep.
Cool. Awesome. So I made a quick slideshow of uh, just like a few slides that'll cover this topic. Hopefully trying to make it a little bit more fun than not, but it's a pretty deep topic in general. So I titled this Maison du Lac because French is cool. Why do we need houses for data by a lake? Because the phrase data lake house kind of sounds unusual in comparison to some other technical phrasing. So why do we need houses by a lake for data? A quick outline of what we'll go over. I'm going to cover some ingredients, and then hopefully we'll arrive at a delicious stew later on. And just like making a delicious stew, it can get a little bit messy, and my intent is to be pretty broad-reaching. I'm not trying to be overly factual or be absolutely correct because a little bit of this is amorphous and kind of depends on how companies have decided to brand their own data lakes and lake houses. But please, if you see something that's worth talking about, don't hesitate to call it out because this is meant to be useful for the group and not just me presenting to a wall. So first, I thought it might be helpful to talk about what is a data schema because sometimes schema gets overloaded. And schema to me generally refers to a blueprint of a database, and it can include tables, column names and types, relationships, constraints. And over here, I have an entity relationship diagram, which is generally how schema or schemata are defined for a relational database. So you have like an amends table or like a users table, and then we can have like all of these different column types that are in here. And then those tables might be related to other tables with lines. And we don't have to go into the specifics of how ERDs work, but the gist is that it provides a way to define the data somehow. What is a data catalog? So a data catalog is a collection of data schema information, which typically is searchable and usable within data workflows. It provides information about what data exists and where it is stored and how it is structured and how it can be used. Uh, Not all the time do we use data catalogs. Say, for instance, inside of a relational database management system like Postgres or MySQL. But more and more, this is becoming a product that people ask for when it comes to certain data platforms that we use to make it so that we can find data and that hopefully we can use it. Sometimes the data catalog itself is invocable, like we can program against it. Other times it's just data documentation. So what is a data query? A data query is a request for data usually performed using an API or data query language like SQL or Cypher or Sparkle. Um, SQL we use with, say, Postgres and MySQL. Cypher, we would use that with Neo4j. Sparkle is used with yet other systems. Typically, a query will leverage schemata to help define what is requested. So it uses sort of the table name or like the column names to help reference what we're requesting. So think of yourself as a user over here on the left, and then you make the data query that arrives at the data somehow, and then it is delivered back to you. And I'm just showing down here a simple SQL query that is selecting every column from the table weather, where the city is Baton Rouge, and the date is 2/12/2025. So what is a data query engine? So the data query engine is the thing that can perform that data query request for you and help complete that work to get it from wherever the data sits. Oftentimes databases include a query engine inside of them. And so sometimes we don't actually know or think about the query engine as being a separate thing from the database, but really it is. So like Postgres has a query engine that's built into the system and helps to navigate how you perform a SQL request against the data. Query engines can also be distinct components, so they don't necessarily have to be inside of the database. They can be a unique product themselves. And examples of this include things like DuckDB, which can sort of create a remote or like virtual in-memory data query engine against data that may not be in a DuckDB database. Another example in the cloud is AWS Athena, which helps to navigate SQL requests over data that's stored in object storage. Uh, so another important concept is extract, transform, and load. So extract, transform, and load, or ETL, is a data processing pattern which involves gathering the data from some data source, modifying it somehow, and then sending it to some data target somewhere. That can even be the same data source, but usually it's a separate data target. So why use ETL? ETL is good for unifying data into a single schema. So think about it. If we have external data sitting somewhere and we want it to live in our database that is a different place, usually we want to kind of get that like triangle data to fit into like a circle hole. So think about like a kid's toy where you have like the blocks that are a triangle or a square or a circle. You have to fit them into sort of the right shaped hole in order for it to live inside of that new box or that new location. Uh, so another example is to think about like if we have JSON data that needs to go into a Postgres database, we probably have to structure it differently. Although you can store JSON data inside of inside of Postgres, but we might need to reformat it a little bit in order for it to live there. Another important pattern to be aware of in the context of data lakes is extract, load, and transform. So this is very similar to what we just went over with ETL, but this is ELT. So we've moved the load part to be the middle or like the second step in this conceptual pattern. So what we do here is we usually have a data source and then we have a data target. So we move the data source into the data target. So we're moving the data into the target directly without modifying it. And then we perform some sort of a transformation later. Um, why would we do this? Why would we want to do this? Or like why try and fit, the triangle blocks into the like circle holes, so to speak. ELT is really good for analytical queries with schemata that are likely to change or that we don't really want to deal with right away, or like things that we don't want to build assumptions around. Um, and also for occasions where we might not know what the target schema is. So we might not know always what we want from the source data. We might be still deciding. And so ELT provides a way to not modify the data and sort of push the transformation to later so that we can make those decisions later. And we have greater flexibility to make analytical decisions along the way. So object storage. Object storage is a data storage approach which involves managing blobs or binary large objects, or just simply objects. Common providers of this include MinIO, AWS S3, Google Cloud Storage, Azure Blob Storage, and there's a ton of other solutions. Usually when we're talking about object storage, we're talking about buckets nowadays. So we have input data, and then imagine that input data being landed inside of a bucket, and then we can get the output data from that bucket whenever we need it. And object storage provides that layer of the bucket for putting things in the bucket, letting it live there, and then getting it back out. Why use object storage? So we still want the data, however, it can be difficult to fit certain data into a unified schema. So for instance, images, etc. So like if we're trying to fit an image inside of a relational database management system, we usually have to store that as a blob anyways, because it's binary data and it's unstructured data theoretically. So we have to put that into the database as a blob anyways. So object storages are intended to be literally a storage zone for just blobs or objects that don't have any structure necessarily. It may also be too time consuming to decide on a schema upfront for all data, as we mentioned with the ELT pattern. These are a little bit different than file systems because they provide a unified API whereby everybody can access the same data. So I think sometimes it might be easy to think about like why not just use a file system to do this very same work. And I think that there's probably better arguments that I can get to in the time, like a short time here today. But generally, it's really great to have a unified API that you can work with and a technology that's dedicated to storing files like this and having them be stored rapidly and retrieved rapidly than say a shared file system can provide. But I think file systems are probably related to this in a way. Workflow engines. So workflow engines are oftentimes the data movers of a data environment. So they provide a consistent way to move data around when working with many different types of data. Um, and many workflow engines make use of what are called directed acyclic graphs, or DAGs. And really a DAG is just think of it as a set of sequential tasks that have to be accomplished. And so once task A here gets done, then B will initiate and complete. And then after it completes, C will then initiate. But we can also have all sorts of different branching mechanisms within DAGs and workflows usually. So why use workflow engines? Workflow engines are often great at completing repetitive tasks which need to take place. They provide sort of a template to accomplish the tasks so that our data can move happily along from steps A, B, and C. And then we can also go back and look at workflow engines to make sure that tasks A, B, and C went right. And if they didn't go right, like if we don't have the data or if the data hasn't been updated recently, we can go back and we can see, oh, B failed for this reason. And we know that because B failed, that C wouldn't have completed because it's a DAG or because it's a workflow engine, and we can go back and diagnose those problems. So now we arrive at data lakes. So we can't describe data lakehouses without talking about data lakes. So data lakes are managed storage solutions for data which very often extract and load data somewhere. Um, Workflow engines usually help accomplish the movement of the data. And they often involve object storage. So think of the workflow engine helping to move this data over here, like the triangle and circle data, into the data lake, which would probably be object storage hosted data. So this could be like images, it could be JSON files, it could be CSVs, it could be Parquet files, all sorts of things could live in here. But there's generally no or very little schema management, and there's not many customizations that come right off the bat. And really, the way I think of data lakes is that really we could call this like a data lake tent. And that's why I put the tent up here, that like you're camping out by the lake, and camping is cool because camping is just a lot of fun. And I'm definitely a proponent of going out and being in nature. And especially if it's by a lake, that sounds awesome. But it can be a little bit rough because we're in a tent and we have to go get everything ourselves. And like if it rains, we have to deal with that. And if there's other problems in the wilderness, like we have to deal with all of that stuff. So it's sort of a like no frills experience with the data lake is how I generally think about it. Think about yourself being in the data lake tent. So data lake houses build upon data lake concepts to avoid what are called data swamps. So data swamps are things that occur because the data that's been transferred to the data lake is not really well governed. Maybe the schema has changed. Maybe there's some kind of unclean practices that are happening that lead to conflicts in how the data operates or how it's being consumed later. Um, and data swamps ultimately become places where people don't want to be because it just gets like life gets too hard. Imagine being in a tent by a swamp, and all of a sudden we have like a bunch of mosquitoes, and maybe it's like hard to make our way through, and maybe we can't do the same types of activities that we wanted to do. Not that swamps aren't really important ecologically. I think they're pretty neat actually. But when it comes to data movement and accomplishing data things really quickly, we want to make sure that we don't arrive at a data swamp. So important things that data lakehouses add are things like metadata management, so helping to manage any metadata that's associated with things. So that could be things like the workflow engines logs, for instance, like telling us about what happened to the data along the way. or other aspects about the data that have to do with like strictly metadata, like data about the data that are part of the data sources somehow. We can standardize the schema, so we can build expectations around what we expect from the data sources, and we can alert ourselves whenever that might change because we're not in complete control of what the data sources do, but we can help keep ourselves informed. We can help govern the data, so we can provide different levels of access to the data. So if we're managing, say, like private data, we can set up different like roles and maybe do like role-based access controls, or we can set up all different sorts of ways of governing the data, as well as deciding when the data is sort of quote unquote dead. So if like the data is no longer useful, we can help to describe that and flag data that's no longer useful or maybe needing a refresh from the data source. We can also build out that nifty data catalog that I mentioned and make that a searchable resource so that we can use that in maybe getting source data information, or we can use that in downstream applications. So how could this look for Moss? So I tried to draw this in like the simplest way possible. So I don't mean for this to look like a kid's diagram, but really I'm hoping to make this very simple so that we can have a good discussion about this. So we could create a data lakehouse which informs the Moss backend and graph database to decouple data extraction from ongoing schema and database deployment. So think about it. If we have all these source data locations that we're grabbing data from, like Alex, OpenAlex, or the ecosystems API, we could have maybe a workflow engine that's grabbing all that raw data and placing it into, say, like a raw zone or like a raw bucket, or maybe a series of raw buckets that help to describe that raw data, which has been unchanged using ELT. And then we can help to prepare that data if we need to, like if we need any sort of tables that, like we were talking about I can't remember if it was the last meeting or the one prior, but where we were talking about how people data or like person data, we might need to deduplicate some of that data. So perhaps that could be like prepared data that we have, which becomes sort of like moss.person or something. And from there, the backend API and or the graph database that we use, which right now I think is Neo4j, we could inform both of those things using the prepared or raw data based on however we see fit, using a query engine of our choice. So this could be SQL queries. I think SQL queries make it really easy, depending on the solution that you use for storing things here, which again would probably be object storage if we're doing the data lakehouse pattern. And then once we have these well-structured, those could be delivered to the front end. Perhaps this arrow is more appropriate to be pointing at the like the GraphDB arrow pointing to front end would be more appropriately pointed at the backend API, and then we just really have the front end consuming from the backend API. And I think that's pretty much it. I can leave this slide up. I can close out the share, whatever would be most helpful.
Leave that slide up. That would be amazing. And before we get into questions, Mark, how much time do you want? Oh, you just responded. Never mind. All right, so we've got probably 10 minutes for discussion questions if anyone has anything.
I have one note that I want to mention. First of all, it looks great. It separates the different concerns we have in our system. And to add to it, Apache Foundation has an open source project called Apache Iceberg, which actually implements this type of the data lakehouse. And one important thing that I think for us very useful is that it supports schema evolution. So it's flexible in terms of changing the underlying schema that we use for our data.
Yeah, Iceberg is really awesome, and I would highly recommend leaning into that as far as a storage solution. Thanks, Guy.
So thank you, Dave. This was an incredible presentation. Really helps iron out a lot of these ideas, and I've taken some notes and I have some research to do.
Yeah, thank you. I think it looks great. I think we have to discuss for the backend graph database and front end. Between backend and graph database, there's arrows going both ways, but is the front end sending any information, for example? And how are we updating the graph database versus the backend API? So is the graph database only going to be a projection of that, or are we actually manipulating the graph database? Because some of the code I've seen so far kind of directly pulls into the graph and manipulates that, as opposed to reflecting what's in the back and what's prepared.
Yeah, good points, Max. I wonder if maybe some of that manipulation that's taking place at the graph database layer could be sort of pushed into the lake if we chose to lean into this pattern.
Mm-hmm. I think we can also, if we do, may I share my screen?
Yeah, of course.
I've been looking at JSON kind of LD, and let me just share my entire screen.
I'll take this opportunity to say 6 to 7 minutes left.
Oh, just quickly showing. So if you have like a context, for example, a GitHub repo, you can predefine the values, and then you have an example repository, which kind of takes from schema.org. So we take things like code repository URL and license and stuff, but then we have our custom definition. And this would, be a really simple format that we can have at the raw stage as well. And there's also JSON LD star just got released, so you can have, so it naturally kind of creates a graph.
Is that is what you just showed there, Max, something that you'd want to put up on the repo as just something that people can see, give feedback on as a PR or an issue?
Yeah, I'll probably have it up probably end of probably not today, but tomorrow sometime. Yeah.
Okay, awesome. That would be fantastic. And see you, Ethan. Good luck with any fires. Yeah, that would be amazing. I think because the stage that we're in right now, I think is Dave's presentation is highlighting is we need to try everything. We're kind of experimenting, seeing which route to take, what architecture is working. So as we come up with ideas, if we can put them up on the repo so there can be direct feedback and discussion there, so we don't get into those infinite discussions, it's beneficial. Any other thoughts?
If nobody else has a comment, I would like to ask a question somewhat adjacent to that topic. What do you think the size of our database will be? How many records, or what's the size in like megabytes or gigabytes? Just an estimation, ballpark.
One of my current iterations has 1 million, and I think that we'll have a lot more nodes than that.
Did you say million?
Yeah.
I just linked to some examples.
I have a script that's pulled 256 repositories and their first degree OpenAlex information, and that's about 50 megabytes. So how many repositories are there on GitHub? Probably 10% of them have DOIs. And those are some numbers we can get. But I think it's going to be a good amount.
Let me try to do some quick estimation.
Are there any more? Go ahead, Dave.
There's a blog post from GitHub that I was going to cite as far as like the size of just GitHub, and they state in their Octaverse report that they have 518 million open source public and private projects, which I'm assuming means repos in the context of the blog article.
And they don't say how big their database.
And they don't say specifically, like, is it forked, for example? Like, how do they count those and stuff?
I can't remember if it's in the article, but I think they do maybe mention something about like uniqueness, but maybe that's specific to like certain aspects of that report. I think it's well into like the hundreds of millions, and probably above that if we think about other hosting services beyond GitHub.
This is a
Is
great.
it
Go ahead, Guy.
private or public repos, the 500 million?
They say public and private.
Okay,
But-
so
I think this is a good, because we are getting to time. I think this is a good item to make as an issue. Let's determine how like very inaccurate how much storage space we would need to store all the metadata of all the projects on GitHub, plus all the metadata of all the papers on OpenAlex, plus all the metadata of all the papers on Papers with Code, plus, and just like this is just some math and some guessing. That would be a lot of fun. And I guess since I'm saying it's a lot of fun, I'm volunteering to do it. So shoot. Does anyone else want to do it?
Can help.
You'll help? Awesome. Thank you. Oh, fantastic. Yilin just posted for the recording, just posted a data set for GitHub metadata, which is only 3 gigs.
but that's just the 5-star ones, right?
Yeah, I guess also they probably don't have the code base. You just have those like text information. I don't know whether they include like the the README stuff as well.
All right, great resource for Mark and me to do this test. Any final thoughts for Dave before I start this recording and restart it for the meeting? And we'll actually comment here for anyone who's listening to this recording and wants to join us on Wednesdays 4 p.m. Find the OSI Slack. I'll put the link in the description and join us and ask to join the production calls, and we'll get you looped right in. Any other thoughts for Dave, though? All right. Thanks so much, Dave. This helped me a lot. I know that much.
Thank you. It was wonderful.